Hello everybody. Today we're going to be talking about two different types of identities for trigonometric functions. It's the double angle identities, sometimes called the half angle identities, but you'll see when we get there. And there's also the angle sum and difference identities. Now before we get into this, I do want to let you know that these identities are a tool for us to use. Usually in high school math, typically, this is not always the case, but in my experience, typically what happens is you get taught how to do a problem and then you just have to kind of follow the steps. This is very much not that. So what I'm giving you and what I'm showing you are tools that you can use however you want. Now I'm going to show you a couple of ways that you can use these specifically to simplify expressions. But you don't have to use them to simplify expressions. You can use them in a myriad of ways, mostly to re-represent some trigonometric expressions as others. So that's kind of the main idea, is you notice a trigonometric expression, and then you can re-represent it in another more useful way. Because of that, this lesson, I guess, this video, is really, I really want you to emphasize within yourself to understand the importance of pattern recognition. So when you see an expression, you're going to have to train yourself to see when to use these identities and when they're useful. And some of these expressions, some of these mathematical expressions which you might get exposed to in your math class, or in math, they might seem totally new, and you might say, "Oh, this doesn't look like anything I've ever seen before." But that's where your pattern recognition needs to come in. That's where you need to see, like, oh, I can rewrite this in this way, which allows me to use this thing, which allows me to use that, and so you can recognize the pattern of the trigonometric function. Anyway, so with that preface out of the way, let's get started. We're going to start first of all with these double angle identities. Now there's three main ones, but just like several other trigonometric identities, like the Pythagorean identities and others, you can manipulate these so that they change, and you can re-represent them, and you can use them in different ways. So these identities are a valuable tool, and again, this first bullet point is just restating the earlier part of the video. So here they are, right? These are the identities right here. Let me use red. So we've got sine of 2a equals 2 sine of a cosine of a. Cosine of 2a equals cosine squared of a minus sine squared of a. And tangent of 2a equals 2 times tangent of a over 1 minus tangent squared of a. The tangent identity, this identity right here, you can actually derive it from the other two identities. Basically, what ends up happening is you can, if you take sine of 2a over cosine of 2a, right, that's going to make tangent. Sine over cosine makes tangent. So this guy right here is actually this guy right here, right? Sine of 2a over cosine of 2a. And then we know sine of 2a here equals 2 sine of a cosine of a. So we replace this with this, right? And that's coming from up here. And then we replace this with all of this, and that's coming from over here. So we end up with this expression, and then finally, if we divide both the numerator and the denominator by cosine squared of a, what ends up happening is in the numerator, because you're dividing by cosine, one of the cosines is going to divide out that cosine, and the other one will turn this into tangent with the sine there. So that would happen in the numerator. and then you also divide the denominator by cosine squared of a, which gives us this will become 1, and then this will become tangent. So that's where you get this, right? So the 2, you get the tangent, right? All of this comes from this process. Okay. Now, when you're using these double angle identities, you can use them in different ways, and let's just show some examples. So one of the main ways, or I should say, what you're doing with the angle identities is you're actually trying to re-represent these mathematical expressions. Sometimes you're trying to re-represent them because they're more useful when they're written one way or another. Sometimes you're trying to re-represent them because you're trying to consolidate a lot of terms. You might have a really messy looking expression and you say, oh, well, I want something that's a little bit more condensed. So you can use the identities in that way. What I'm trying to say here is you need to know the identities kind of forward and backwards. And you need to be comfortable knowing that sometimes you're going to have sine of 2a, and then you have to convert that into 2 sine of a cosine of a. And sometimes you're going to have 2 sine of a cosine of a, and you're going to convert that to sine of 2a. So let's start with an example, just so you can see what I mean. So here we have sine of 120. So we can use this identity to evaluate. In this case, we can evaluate sine of 120. If we don't have a calculator, we can still evaluate sine of 120. And so let's say, you know, your mind is blanking out, you can't really remember the unit circle, but you do remember your special right triangles, and you know sine of 60, and you know cosine of 60, and you know the 30, 60, 90 triangle, etc. But that doesn't help you with sine of 120 because you maybe blanked out on the unit circle. So we can use this identity, right? This is a tool, and we can say, well, you know what? 120 is 2 times 60. So sine of 120 is the same as saying sine of 2 times 60. Okay? And this is meaning the our a, so if we're going to use this guy, right? Sine of 2a, sine of 2 times 60, that means a is 60. And that's going to mean that we can actually re-represent, we can actually take sine of 120, re-represent it as 2 times the sine of 60 times the cosine of 60. Right, so sine of 120 becomes 2 times sine of 60 times cosine of 60. Then, using your special right triangles, you might remember, oh, you know, or you might have to draw out the special right triangle, right, the 30, 60, 90. But you say, oh, I know that sine of 60 is root 3 over 2. And I know cosine of 60 is a half. So this is going to be 2, right, that's this 2 right here. So 2 times, and then sine of 60, that's root 3 over 2. Okay, so that is this guy. And then times cosine of 60, which is a half. Okay, so we've got 2 times a half, which is just 1, which means it's just root 3 over 2. Right? So sine of 120, remember this is what we started with, sine of 120, maybe if we didn't know, if we forgot the unit circle, we can use our double angle identities to kind of make up for the fact that we forgot the unit circle, and you can still evaluate this. So that's why we mean it's just a tool. It's another tool you can use. So this would be the final evaluation, right? Root 3 over 2. That's so second example. Let's say it says use the identity to simplify expressions. Cosine of a plus sine of a times cosine of a minus sine of a. So if we notice this expression, might see that you've got a pair of binomials, right? So you've got two parentheses, and each parenthesis has two terms in it. Each set of parentheses has two terms in it. And we're actually going to multiply these out. Now, if you're new to this, it's not expected that you know to multiply them out, right? You're not going to see this and be like, oh, I should multiply them out. It's definitely something that you get a feel for just by doing it enough times. So you will see this, and for example, in myself, I noticed that they both have cosine of A, they both have sine of A, and their operations are different. One's plus, one's minus. So that, to me, that activates my pattern recognition saying this is going to be a difference of squares, which means if I multiply this, I'm actually going to get a really nice expression where normally I would have a middle term, right? You would end up with a trinomial if you multiply two binomials. But because this is going to be a difference of squares, I know that this is going to look nice. It's going to have just two terms at the end. So we can go ahead and multiply this, and that'll get us cosine squared of A minus sine squared of A. Okay, now I did just skip a bunch of steps, but that's basically what you're going to end up with. So cosine squared of A minus sine squared of A, and you know what? This, I recognize, that's the double angle formula, that's the double angle identity for cosine of 2A. So this is actually cosine of 2A. So definitely using my pattern recognition here, and then continuing to try and notice when I can use different tools. So I used the difference of squares knowledge that I had here to recognize this pattern, and then once I had this, I knew that that was cosine of 2A because that's the double angle identities. So that's what I mean. You have to get a feel for it. You have to use your pattern recognition, and it does take a while. You have to expose yourself to this repeatedly if you want to get real proficient with it. Alternatively, if you have the ability to have a note card with this on it, that kind of alleviates some of that pressure. But there you go, right? Not every class is going to let you have a note card on that stuff. So your mileage may vary. Okay, last example. So this is a slightly more complex example. By more complex, it just has more steps in it, of simplifying expression. So again, it's just an exercise in, number one, pattern recognition, so just recognizing different patterns, but also it's an exercise in being creative, trying things out, and sometimes it works, and sometimes you end up at a dead end. This is one of the things that math books really are not good about, because a lot of times math books, they don't show how people can get stuck. They just say this is how you do it. Where a person that's doing it in real life, someone who might be simplifying this in real life, they might try a couple of different things, and maybe get into some dead ends, right? Some of those things that they try will be dead ends. And that's normal, that's okay. Too many students think that, oh, I have to do it right immediately. That's not the case at all, right? That comes naturally just through developing your skill and just practicing over and over. So for here, okay, one thing you can notice is that I've got a sine over a cosine, so you might start thinking, okay, I'm looking for a tangent maybe. Also, I'm noticing that I've got two sines on the top, but they're different values. And so that might mean, you know what? I want something that's going to be the same value. Also, I'm noticing a 25 and a 50, and 25s and 50s tend to be very related. So I noticed, oh, you know what? 25 and 50 is double of 25. If there's some way that I can double this, then that's what I want to do. Right? So I'm noticing these different things. I'm noticing sine over cosine, which means there's going to be some kind of tangent I'm predicting. And I'm noticing this 25 and this 50, which I'm assuming I can make use of that and relate them in some way. So how can I do this? Well, I know that if I have the sine of 65, that's the same thing, right? This is my problem right here, right? I have a 65. That really doesn't fit the pattern. So I want to say, is there a better way that I can write sine of 65? And the answer is, right, sine of 65, using either your knowledge of triangles or your knowledge of the unit circle, you know that sine of 65 is actually the cosine of 25. So we actually have here 2 times the sine of 25 times the cosine of 25 over the cosine of 50. So now I can see this and I notice, you know what? This is the right side of the double angle identity for sine, which means that this is actually equal to sine of 50, right? So sine of, if I'm seeing this, right, this right here, which I'm circling right now, 2 times sine of a number times the cosine of the same number, which is what I have here, right? 25 and 25 taking the place of a, or alpha, then I know that that's actually equal to sine of 2a. So I'm actually using this in a backwards way, which I actually did here too, actually. So anyway, 2 sine of 25 cosine of 25, I recognize that as this. I can replace this with sine of 50. Like this. And then over cosine of 50. And then this I can reduce even more, because sine over cosine of, if they're the same argument, then that's going to be tangent. That's tangent of 50. Next, we're going to show you the angle sum and angle difference identities. I'll be back with you in just a moment. Okay, angle sum and angle difference identities. So just like before, there's 3 main identities, one with sine, one with cosine, and one with tangent. In these identities, you've got 2 different angle measures, which are expressed as usually they're expressed as one value. Not always, but usually. So here we see a plus b or a minus b. Normally there's just one number in here, so it might be like sine of 30 or something. Okay, but it's split up into a and b so that you can recognize how they fit into the other side of the identity. Also, in each identity, you'll notice there's a plus and a minus sign, or a plus or minus sign, and its orientation is relative to the plus or minus sign that's in the sign. So, for instance, notice how on this one, you've got a plus minus with the plus on top, and here you have a plus minus with the plus on top. So what that means is, if this is a plus, this will also be a plus. If this is a minus, this will also be a minus. So these 2 signs should match. Over here in the cosine, for instance, as another example, here you have a plus minus with the plus on top, and here you have a plus minus with the minus on top. And what that means is, if this guy's a plus, then this guy's going to be a minus. And if this guy's a minus, then that guy's going to be a plus. So it's an inverted relationship there. Okay, and then tangent, because tangent is kind of derived from the sine and the cosine put together, it actually has both. So for tangent, you've got the plus minus on the top, and then the minus plus on the bottom, right? So the top or the numerator will have the same sign, the same operator as this one, and then the denominator will have the other operator from whatever the argument is. So now we can use these to evaluate and break up trig expressions, just like how we did with the double angle formulas. The situations where you use these are slightly different. Usually when you're in pre-calculus, you mostly use, in my experience, they're mostly used just to evaluate. So let's jump into some examples. Okay, I've got 2 examples for you. So let's say that you have sine of 75. Okay, so ignore all this right now. Let's say you have sine of 75. And you're supposed to evaluate what is the sine of 75. And you don't have a calculator, you don't have access to a computer, but you do know your unit circle, in other words, your coterminal angles and that kind of thing, your your reference angles and things. And you also know your special right triangles, the 45, 45, 90 triangle and the 30, 60, 90 triangle. And you're expected to evaluate sine of 75. Well, that might seem like an impossible task, but if you know the angle sum and angle difference identities, you can actually split up this 75 into more useful pieces. So for instance, 75 is 45 plus 30. And the reason why we want to split it up that way instead of something else like 60 plus 15 or 70 plus 5 or 80 minus 5 or something like that is because 45 and 30 are both values that occur in special right triangles. So if we have the sine of 45 and the sine of 30, we can use special right triangles to actually evaluate both of those things. So we only start with the sine of 75, and it would be up to us then to split up this 75. We say, oh, well, sine of 75 is the same as sine of 45 plus 30. So you would then re-express it this way. Now, sometimes it is possible that you have multiple ways of expressing something like this, right? So you might have sine of 90 minus sine of 15 or something like that. And if you know what the sine of 15 is, then you can totally use that. This part here is going to depend on whatever is easiest for you to calculate. But we want to create an addition or a subtraction that equals 75. So now we have this addition here. Now using the angle sum identity, we can say sine of alpha plus beta, so right here, right, sine of alpha plus beta, equals the sine of alpha times the cosine of beta plus the cosine of alpha times the sine of beta. So we're taking this and we're just replacing, right, where there's alpha, we're going to put 45, and where there's beta, we're going to put 30. So sine of 45, cosine of 30, sine of 30, cosine of 45, and then you use, from here, you can just use your special right triangles. Right? Sine of 45, that's root 2. Cosine of 30, that's root 3 over 2, and so on and so forth. You get all these, and then you simplify it or re-express it or whatever. You can mess with it after that. So, again, the thing here is when you see a 75, don't think of it as just a 75, right? Numbers are made up of other numbers, and you get to choose what that 75 is. So the 75, you can break it up in all kinds of different ways. Everybody is going to have their own way that they're going to break it up, the way they're going to understand it. It is very common, to use 45 and 30, but that's something that has to come from you, right? That's something that you have to understand. And it's not like every time you see a 75, you're going to do that. It's totally dependent on the situation. Okay, example 2. I know I ramble, you guys. I'm sorry. I'm going to try to speed it up a little bit. Okay, example 2. You got cosine of 15. Okay, so here, this is what I'm talking about, right? Cosine of 15. You can split this up in multiple ways. And in this example, I chose to split it up into cosine of 60 minus 45. However, some people might see 15 and they say, oh, that's 45 minus 30. And you can totally do that, right? Instead of doing 60 minus 45, you could do cosine of 45 minus 30. And that's still the same thing. You're going to get the same answer. So it really is up to you and up to your understanding, your creativity. How do you see 15? Do you see 15 as 60 minus 45? Do you see 15 as 45 minus 30? In any case, for the purpose of this example, we're going to use this. So we've got 60 minus 45, and then we're just going to go right up here. We're going to replace, right, everywhere where we see alpha, that's going to be represented by 60, right? So this would be 60, this would be 60. And then everywhere where there's beta, we're going to put 45. So 45 here and 45 here. And because this is a minus, that means this one will be a plus. Because if we look up here, this one has a plus minus with a plus on top, and this one has a plus minus with a minus on top. So whatever this one is, this will be the opposite. So we can replace that, and then using our special right triangles, we can just re-express these. We can evaluate them, and we can leave it like this. We can factor out the root 2. You know, it's up to you. But these possibilities, you have to be aware of them, and you have to be able to do them when they're useful, when it's useful for you to do them. So I have a challenge for you. I'm going to challenge you to show why tangent, why is this equal to this? Okay, why is the angle sum and difference identity for tangent equal to this? Okay, and I want you to do it based on sine and cosine. So tangent is equal to sine over cosine, right? So I want you to show and do that. Okay, so you've got these new tools available to you. As you're practicing them, it's pretty useful if you have them as a reference. And ideally what you want to do is, if you're practicing them, if you're using them for your homework or for whatever, if you're using these identities, what I would do is have them actually written out somewhere where you can reference them. And then just keep doing it until you don't need to do it, until you don't need to check it, until you don't need that note card anymore. Anyway, I hope you have a wonderful day. I'll talk to you later.